Again, and welcome to another edition of Algebra 2 Notes with Miss Faust. Today we're going to look at graphing square root and cube root functions, but before we do that, let's have another quick joke. Why was the math book sad? It had too many problems. Okay, good. Now that we've had a good laugh, let's go ahead and get started looking at some of these graphs. So, again, we're in Unit 6. This is lesson 10.2. And our essential question is, how do you graph square root and cube root functions? So I've got some space for your questions here, notes here. So our first function here is y equals the square root of x. And really, I probably should be using function notation here. Both of them mean the same thing. And this is what we call our parent function for this set of graphs. So our square root functions always have the same shape. You can put the little 2 up there or not. It's up to you. When we graph these square root functions, we want to pick our x values kind of carefully because otherwise we'll end up with a whole bunch of decimals. So I pick some x's over here, and if you think about what the square root of 0 is, grab a calculator if you want, but the square root of 0 is just going to be 0. The square root of 1 is 1. The square root of 4, so what multiplies by itself to get 4? Well, that's 2. The square root of 9 is 3. So that shows us some of our values for this graph. So 0, 0, I'll start here. 1, 1 is here. And then the next one goes all the way out to 4, 2. So 1, 1, and then 2, 3, 4, and up 2. You can see by the time I get to 9 and 3, I'd be way out here on my graph. But I don't need that much of it to show you the parent function, and so that you can see really the points we're going to use as reference points. And those are always going to be this 0, 0, and 1, 1. So we're going to look at how those points move when we look at transformations of this function. So this one is again at 0, 0, and that one's at 1, 1. And those are going to be the reference points. This particular graph, just having 2 of them is enough because it's always just this half curve shape. Okay, so then we can look at that. Hopefully you can see for this one the domain, well, we never have anything less than 0. So you can't take the square root of anything and get a negative number. So our domain for this is 0 is less than or equal to x is less than infinity, because you can put in a really big number and still get the square root. And same for the range. It starts here from 0 and it keeps going up forever. It doesn't go up very fast, but it does go up forever. So the range is 0 to infinity, again, for the y's. Okay, so that's our square root parent function. Our cube root parent function looks a little bit different, and we looked at that in class last time, so this is our cube root function. And again, we're going to consider our x values kind of carefully because we don't want crazy decimals. While I know you guys love decimals now, I don't want you to be having to use them all the time when it's not necessary. And this is a case where it's not really necessary. So if we think about the cube root of negative 8, so something that multiplies 3 times to get negative 8, it's negative 2. Oops, let me do this in a different color. Cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. If you don't believe me, you can always check those in a calculator. And then again, what we can see is that the x's get really big really fast and really small really fast. So we're not going to graph a whole bunch of them when we do this. Negative 8, negative 2 would be way back here and down here somewhere. Negative 1 is right here. And remember, from there, it curves way out that way. So I'm just going to put an arrow like that to show that we're going towards that negative 8, negative 2. Then we go to 0, 0. Then we go to 1, 1. And then we go way out to 8 and 2, which would be out here somewhere. So what I do for that is, again, I just make that shape going out towards that 0.82. And again, this should look familiar. It should look kind of like the cubed function, the cubic function. It's just flipped over the line y equals x because we're working with these inverses now. So this shows us the 3 reference points we're going to use for this function all the time. We're going to use this negative 1, negative 1. We're going to use this 0, 0, and we're going to use this 1, 1. And then after that, you're just going to draw these curves that go in both directions. It's important to make them curves because otherwise they'd be a different type of function. But as long as you're showing that it's curving on the ends like that, you're going to be fine. For our purposes, we don't need really precise graphs. So these are good sketches. Domain, arrows on both ends. So domain is negative infinity to infinity. Range is also negative infinity to infinity. Again, really, it doesn't get very big or very small fast in the y direction, but it does go on forever in those directions. Okay, so those are our basic functions. And what we're going to do now is we're going to look at how we can transform them into some other functions. So in order to do that, let's just take a look real quick first. I just want to show you some examples of how these graphs move, and then we'll formalize it. So this is our square root function. If I take that square root function, I can slide it left and right. And notice when I slide it left and right, I still only have I still only have half of a parabola, a sideways parabola. And notice here, the reference points move together. So when I slide it back and forth like that, those points move together. When I slide it up and down, the same thing happens. If I move it up there to 2, right, then it went through 0, 2, and 1, 3. So it went over 1 and up 1. I didn't do any stretching of it yet. I just did back and forth, left, right, and up, down shifts, and those work the same way they have in all the other functions we've seen. And so then the stretch is what might look a little bit different. Oops, I made it negative. I meant to make it positive first. So there we have a stretch of 2. There we have a stretch of 3. We had a stretch of 3. There we have a stretch of 4. There we have a stretch of 5. And you can see all it does is it makes it go up faster than it did before. And if my A is negative, then it still stretches, it just stretches in the opposite direction. And of course we can put all of those things together. So if my stretch is 2 and I shift it to the left 5 and I shift it down 2, right, then I can find the equation for that function. Okay, so let's take a minute now and look at how those formal transformations on square root functions work. So back up to the top here. The general form is going to be y equals the square root of x minus h plus k. And as I said before, all of these are going to work the same way we're used to. So h is going to be a horizontal shift. And if it's minus h, it moves right h units. If it's plus h, it moves left h units. K is going to be a vertical shift. If it's minus k, it moves down. I don't know why I did minus first. Oh well. If it's plus k, it moves up. And the point that you're really looking at when you're looking at these two things is that 0, 0 point. That's the reference point that's going to move left, right, up, or down first. So we move our reference point. Then we look to see whether we have something on the outside. I must have another color in here. And if we have something on the outside, A is our vertical stretch. So to look for that to show up, we go over 1 to the right. And then we go up or down A from our translated 0, 0. So this point gets moved first. Then from wherever that point ended up, we go up, down, left, right. So let me just show you that in a couple of examples. And then we'll go on and we'll look at cubic functions. Okay. So example 1, graph y equals 3 square root of x plus 4. So I like to always start with my parent function. You don't have to do that, but it just helps me to think about what's going to come next. So there's my parent function, 0, 0, 1, 1. Again, that came from this graph right here. So I can see where my 2 reference points are, and then I can think here about what's going to happen. So I look at this +4 on the outside. The +4 on the outside means it's going to go, oh geez, I'm changing this problem because it's not going to fit the way I just drew it. I'm making it -3x. So +4 means it's going to go up 4 units. And then the -3 means it's a vertical stretch of -3. Notice it doesn't go left or right at all. There's nothing inside the parentheses with that. So what I can do is I can take my 0, 0 reference point. I move it up 4, so I go 1, 2, 3, 4. This is why I changed the second part. So my 0, 0 goes there to 0, 4, because it went up 4. And then the vertical stretch of -3 means that when I go over 1 from this point, I have to go down 3. So that one also ends up at 1, 1. That's my other reference point. But this one goes like that and curves down. Okay, and then for that one, the domain would still be 0 to infinity. I'm going to write it in this format just because that's a little bit easier to write, a little bit shorter. And the range now, notice that the graph is starting here at 4 in the y direction and going down forever. So it's going from -infinity to +4. That's our range. And again, that's because this was moved up 4 and then it was flipped, so it went down instead of up. Second example for your viewing pleasure. Graph y equals 2 square root of x minus 3 minus 1. Just making sure I'm giving myself enough space here to do this one. So here's my original function, 0, 0, 1, 1. That's what I have to move. Think about how I'm going to move it. This time I have this -3 on the inside, so I'm going to go right 3. I have this -1 on the outside, so I'm going to go down 1. And remember, I'm going to plot that point first. That's my transformed vertex point. And then finally, whoa, if my camera doesn't fall off of my desk. Hold on 1 second. Technical difficulties. Stay tuned. There we go. Much better. Okay, so sorry, where was I? So my 0, 0 point goes right 3, down 1, and ends up right there. So that reference point is at 3, 1 now. Then this 2 on the outside means I have a vertical stretch of 2. So from this 3, 1, I'm going to go up 2 and over 1 and draw in my line. Okay, and again, then I always want to just consider my domain and range. The reference points, that one was at 3, 1. That one's going to be at 4, 1. Or that one was at 3, -1. What? Come on, Miss Fast. You can do better than that. 3, -1. Okay, domain then, nothing over here until we get to 3. So it starts at 3 and it goes to +infinity. Range, nothing down here. Starts right there at -1. Goes on to +infinity. Okay, so you can see we end up with just these little half curves when we do square root functions. We also then can think about transformations of cube root functions. I'll do this and then I'll show it to you on the computer this time. I mean, this is the computer. Whatever, you know what I mean. And I made that skinnier, but that's okay. You can make it the size you need. Again, we start with y, our general form. This time we have a cube root instead of a square root. And I'll let you in on a little secret. X, h, and k do the exact same things to the functions. The difference is we start with a different parent function. So h is a horizontal shift. Minus h means it goes right. H plus h means it goes left. H. K is a vertical shift. I know some of you right now are like, I can't read that green pen. I don't like it. That's okay. I won't use it very much. Up or down, K units. And A is our vertical stretch. Vertical stretch. So that means from your new center point. So here in this case, it's the 0, 0 that we move first. We move that 0, 0 reference point, and then from there we go right 1 and up or down K, or A, sorry, A, and then left 1 and the opposite way, down or up A. And again, we'll look at examples of how that works. Speaking of examples, let's look at one right now. Example 1, we're going to do y equals the cube root of x plus 2 minus 4. So again, I'm going to start with my parent function, which goes through 0, 0 and 1, 1. And there, and again, this is where you want to be a little bit careful. People are tempted to make a straight line like that. It's not a straight line. This cube root part tells us it's got to be this curve. So we're taking that curve and we're moving it. So we look at this plus 2. Plus 2 means that our whole thing is going to shift left 2. And again, we're going to start with that center point. And our whole thing, because of this minus 4, is going to shift down 4. So I think about that center point moving left 2 and down 1, 2, 3, 4. So that's where my 0, 0 was. It went left 2, down 4. Now I notice out here I have no stretch. So what that means is that these 2 points are also just going to move left 2 and down 4. Or it means that from here, when I go right 1, I just go up 1, and when I go left 1, I go down 1. I connect them with that nice curve. I'm not looking for exact with these. Oops, that's not 0, 0 anymore. Shouldn't try and do two things at once. That is now negative 2, negative 4. Hey, that corresponds to that. Left 2, down 4, right? That tells us where our new center point goes. So then this point would be negative 1, negative 3, and this point down here is negative 3, negative 5. So we can see those are our reference points. Our domain for this one is all real numbers, or negative infinity to infinity, and our range is also all real numbers, or negative infinity to infinity. Cube root functions, that's always the domain and range. In that way, they're a teensy bit easier than square root functions. Okay, so let's look at one more example of this. If I can again get this, I don't know what, I can't quite get it right. It's bugging me today. Okay, so one more example. Y equals negative 1/2 cube root of x plus 3 minus 1. So again, we break that down. We start with this. This tells us we have to go left 3. X is lie, so if it's plus, I go left. That minus 1 tells me that, again, I'm going to go down. This time I'm going to go down 1. So from that, you might already see that your center point is going to now be at negative 3, negative 1, that center reference point. And then our stretch in this one is negative 1/2, which means that from this center point, I'm going to go right 1 and down 1/2. And I forgot to draw in the original function, so let me do that quickly so that we can see where this ends up. So original one, there, there, and there. Loop. So our new one is moving to the, sorry, it's really distracting to have upside down words. You know what? Let me just get rid of that. Much better. Less distracting for me and you, I'm sure. So left 3, down 1, negative 3, negative 1, first reference point. Stretch of negative 1/2. So when I go over to the right 1, I go down 1/2. And when I go to the left one, I go up 1/2. And when I connect these, they will look something like that. So this point now is at -3, -1. That point is at -2, -1.5. And this point is at -4 and -0.5. So you can see it's just squished it together a little bit from what we've had before. So hopefully you can start to see how all of these look very similar to the ones we've done before. I want to just talk you through another graph or two. So let's look at this, and let's just say, for example, that we had a graph that looked like this. So let's say we had this function on top of it, and we're trying to figure out the equation for that orange function. So the first thing we have to do is we have to recognize that the orange function is a cube root function. So that big sort of stretched out S shape is a good indication that you're looking at a cube root function. So then, once I know, that I'm looking at a cube root function, I compare it to this red one. And I want to look first for where my center point went. So my center point was at 0, 0. Now it's gone up here to, what is that, 4, 3. Right, so my center point moved to 4, 3. I'll put that point in if I can. 4, 3, right? So I've got a point there. So I know that my transformation took me 1, 2, 3, 4 units right and 3 units up. And then the other thing I can do is from there, if I go over 1, I look for where my reference point is. So when I go over 1, so from 4 over 1 is going to be 5. So I'm going to stop this when I get to 5 for you. And at 5, it's at 5, 5. So I'll put that point in. And that's actually enough that we can now write the equation for this function. So again, remember we have this point and this point. And let me just move that out of the way and show you what our equation then would look like. So our equation, we know it's a cube root function, right? So it's got to be in that form. So it was shifted right 4, it was shifted up 3, and it was stretched by 2. So my equation is going to be cube root of x goes in there. Well, right 4 means this needs to be a -4. Up 3, so +3 at the end. Notice I carefully put the +3 outside the root, not inside, because it would do something different if it was inside, it would be moving it left or right. If it's outside, though, it's moving it up or down. Sometimes it's helpful to put a little tail on your square root or your cube root just so you know where it's ending. And then finally, because it's stretched by 2 out here in front, I'm going to put 2 times the whole thing. And again, you want to be careful to make sure that 2 and that 3 are clear and separate when you write them. So our function for this is 2 times the cube root of x minus 4 plus 3. Questions? Write them down. Ask me in class next time. Thank you very much. Have a wonderful day, and I will see you again soon. Ciao.